Hello students, in the last class we had studied row operations and column operations. Now in this class we are going to use these operations to find out inverse of a matrix. So basically in this class we will be using row operations only to find out inverse of a matrix. And to explain this concept I am going to take up questions from exercise 3.4. Second question, a matrix is given, a square matrix. Now to find out the inverse of this matrix, we want to use row operations. So here we have to understand that to use the row operations, our matrix equation should be of this kind. So if the matrix equation is of this kind, we are going to perform row operations on matrix A and on the identity matrix A. So what is our idea of performing the row operations? With the row operations, the matrix A, which is this, has to be converted to an identity matrix. So our idea is to convert this into an identity matrix. So what we need here is a matrix of this kind. As you can see here, when we are using row operations, we will use row operations and obtain the columns one by one. Because there are two columns in this matrix, we can start with any column. I will go in the sequential order. I'll try to convert the first column elements of the matrix 2 and 1 into 1 and 0. How is this possible? So let us first of all write down the matrix equation, which is matrix A is identity matrix into matrix A, because in this matrix we are not performing any row operations. It is written as such. Now this is matrix A. We want the first element to be 1. So we can interchange row 1 and row 2, and the new matrix which is obtained is this. The same row operation we'll perform on the identity matrix also, and the matrix obtained is this. So in this matrix what we have obtained is this 1. Moving down the column, this element has to be converted to 0. This element is present in the second row. So that means some changes in the second row have to be done. In this case we have only 2 rows, so some changes in row 2 with respect to row 1. What can be that possible change? R2 minus twice of R1. You can see here 2 minus twice of 1 will make this element 0. So let us perform this operation. Now while we are performing this operation, we have to be very careful with our calculations and with the positive and negative signs. If there is one such error in our calculation, the inverse of the matrix will not be correctly found. So because row 1 remains the same, changes in row 2, this minus twice of this makes it 0. This minus twice of this gives us minus 1. Here again there is no change in row 1. Row 2 will change by this rule only. This minus twice of 0 is 1. This minus twice, like this. So after this operation you can see that the first column of the identity matrix has been obtained. Now in the next column we want 0 and 1. I will prefer to convert this into a 1 first. Again, because this element is present in the second row, so some changes have to be done in the second row. If we multiply the second row elements by minus 1, this element will become 1. So let's perform this operation. The first row again does not change. The second row performing this operation becomes this. Likewise on the right hand side, the first row of the matrix does not change. The second row will have opposite signs like this. Now this element has to be converted to a 0. Then this matrix will convert into an identity matrix. This element is present in row 1. So some changes in row 1 with respect to elements of row 2. Row 2 does not change. So R1 minus R2, R1 minus R2, R1 minus R2, 0. So the identity matrix has been obtained. But we do not stop here. We perform the same operation on this matrix as well, where R2 matrix does not change, and R1 matrix, this minus this element, this minus this element. So we started with an equation of the kind A is equal to IA. Finally, what we are getting here is identity matrix, which is some matrix multiplied by A. We have studied in the previous classes also that a matrix multiplied by its inverse gives us identity matrix. So this is how we say that this is the identity matrix. Hence the identity matrix is this. Two things that have to be taken care of. First, this is the equation to be used for row operations. Whenever row operations are used, corresponding columns have to be converted into zeros and ones. Okay, next we'll take up question number 12 from this exercise. A square matrix of order 2. So once again, for row operations, the matrix equation to be used is, matrix A is I into A, where we make changes in matrix A on the left side and the identity matrix on the right hand side. Our aim once again is to convert this matrix into an identity matrix. So we want the first element to be 1. One of the operations that we can perform here is divide R1 elements by 6. If we do this, dividing by 6, the first row elements have changed, the second row elements remain the same. Performing the same operation here, dividing each element of row 1 by 6, this matrix is obtained. So the first element of the matrix has been converted into a 0. Next we will see how to convert this element into a 0. The element is in the second row, so second row plus twice of first row, minus 2 plus 2 times 1 will make it 0. So performing this operation, this is 0, this minus 1 plus, please do this operation on the right hand side so that you can be sure that the operations we are doing give us the correct result. This is the operation we are performing. We can do the calculations mentally as well, but wherever we get rational numbers, we should be careful. So I am doing it that way. R2 is 1 and R1 is minus half. The result gives us 0. So here we obtain a 0. Let's do this operation this side also. The first row remains the same. The second row, this plus twice R1 is 1 by 3. This plus twice R1 remains 1. After this step, you will notice that elements of a row have converted into a 0. If this happens, that means the inverse of the matrix does not exist. In this case, you can write down, since elements of R2 are all zeros, of A does not exist. While performing these row operations, we can initially only also check whether the inverse exists or not. There is a shortcut method for, especially for a 2 by 2 matrix. If you cross multiply 6 into 1, 6 minus product of this element, which is 6. If this result comes out to be 0, then we can know in advance that the inverse of the matrix does not exist, which we find out after performing 2 operations. Next we'll do question number 15. So for question 15, I'll straight away write down row operations. The equation is this, and the matrix equation is 2, 2, 3 minus 3, 2 minus 2, 3, 3, 2, which is equal to identity matrix multiplied by A. So we want this element to be 1. This element is in first row. So let us perform this operation. See, with this operation you get 2 plus 2, 4 minus 3, 1. So we can easily get 1. So performing this operation, here is 1. Minus 3 plus 2 minus 1, minus 1 plus 2, 1, 3 plus 3, 6, minus 2, 4. So the first row elements, the second row elements remain the same. Performing the same operation on the identity matrix, we get 1, 1, minus 1. Second and third rows remain the same. So our next step is to obtain a 0 here. This element is in the second row. So second row minus twice of first row. You can see here twice minus twice of 1 will give us a 0. So the first row does not change. Making changes in second row, this minus twice 0. This minus twice is also 0. This minus twice of 4 is minus 5. Third row elements we'll write a little later. On the right hand side, the matrix has first row as the same. Performing this operation on the second row, this minus twice, 1 minus twice, and 0 minus twice gives us this element. Now moving on to the third row. The third row is 3. And this element in the third row can be converted to a 0 if we have 3 minus 3 times the first row. So the corresponding operation would be R3 minus 3 times R1. Performing this operation here, 3 minus 3, 0, minus 2, minus 3, minus 5, minus 2 minus 3 times this will give us minus 10. Performing the operation here, this minus 3 times, this minus 3 times, and this minus 3 times gives us 4. So after these row operations, we have obtained the first column. Now in the next column, we want an element 1 here. So if we think that we can interchange the second row with the first row, like here, and if I write only the matrix on the left hand side after this operation, we will get 0, 0 minus 5, 1, 1, 4, 0 minus 5 minus 10. Here no doubt a 1 has been obtained, but column 1 gets disturbed. Column 1 is 1, 0, 0. It no longer remains the same. So any operation that changes the previously obtained zeros or ones is not a valid operation. So this operation will not be used. What is the other thing we can do? We can interchange here R2 and R3. So that ways, first row 114, second row is 0, minus 5, minus 10, next 0, 0, minus 5. On the right hand side we have 1, 1, minus 1, minus 3, 4, minus 2, minus 1, 2 multiplied by matrix A. Now this element can be easily converted into a 1 if we multiply row 2 by minus 1 by 5. So here, first row 114, second row performing this operation, dividing by minus 5, this is obtained. Third row is this. On the right hand side, the first row does not change. Minus 1 by 5 times R2 will make the second row 3 by 5, 3 by 5, minus 4 by 5, and the third row remains unchanged. So now in the second column, this element is left, which is in the first row. So performing an operation like R1 minus R2, the first row will become 1, 0, 2. Second row does not change. Third row does not change. On the right hand side, R1 minus R2, this minus this, 2 by 5. This is also 2 by 5. Minus 1 plus 4 by 5 will give us actually minus 1 by 5. The second row is same. Third row does not change. So after these many operations, the first two columns have been obtained. Our next aim is to convert this into a 1. Now to convert this into 1, because the element is in the third row, if we multiply the third row elements by minus 1 by 5, this multiplied by minus 1 by 5 will become 1. So the matrix on the left hand side, 1, 0, 2, 0, 1, 2, 0, 0, 1. On the right hand side, the matrix is 2 by 5, 2 by 5, minus 1 by 5. Second row is the same. And the third row we are dividing by minus 5. So the third row elements are this. Now in the third column, 1 is already here. Next, let us convert this into a 0. If you want, you can convert this also into a 0 first. That choice is yours. I am converting this into a 0. So R1 minus twice of R3. So the first row is 1, 0, 0. R3 will not change. And R2 will write down a little later. Now to write down elements of this, there is a lot of calculation work. So this I am going to do in rough. R1 minus twice R3. So R1 minus twice R3, which is 2 by 5. This on simplification gives minus 2 by 5. Next element, 2 by 5 minus twice of R3, which gives 0. Next element, minus 1 by 5 minus 2 times minus 2 by 5. This gives us 3 by 5. So the first row has been obtained. The third row does not change. And now for the second row, we are performing an operation in the same step. The element is in second row, so performing an operation for second row as R2 minus twice R3. 2 minus twice of this will give us 0. So this way, identity matrix obtained here. Now this operation is R2 minus twice R3. Again, 3 by 5 minus twice of 2 by 5 gives minus 1 by 5. Next element, 3 by 5 minus twice of 1 by 5 gives 1 by 5. And lastly, minus 4 by 5 minus twice of minus 2 by 5 gives 0. So at this stage, an identity matrix on the left side has been obtained. We have matrix A on the right hand side, and we know a matrix when multiplied by its inverse will give us identity matrix. Hence we get to know that A inverse is the matrix with these elements in the first row. These are the second row elements, and here is the third row. The operations that we have used here are not unique. The way I have solved this question is not a unique method. The operations may vary from person to person. So the operation that comes first into your mind has to be used, keeping in mind that the operation is a valid operation. Next, some more small things you have to keep in mind is, whenever we are performing any row operation, suppose here we forget to write down matrix A, then on the left side is a matrix, on the right side is a matrix, and you can see for yourself that the two matrices are not equal. So if this A is not written here, then we commit a logical error. So we have to ensure that matrix A is written in every step. Next important thing to take care of is, we are performing these kinds of operations where we deal with fractional numbers, rational numbers. So mentally, if anybody can do this calculation, you're most welcome. But I would suggest that we need to do it here in the rough column, so that we get to know what is the exact result and write down the exact result here. At any point of time, if this element is written as +1, the same error will be carried everywhere and the final inverse will not be correctly obtained. So, matrix A has to be written in every step. The row operations have to be valid operations, and then the calculations have to be done very, very carefully. So we have solved the 15th question. Now in the next class, we shall be solving few questions using column operation.